Next, I'd like to talk for a moment about the concept of resolution in remote sensing, which is similar to the concept of scale in geography. And the trade-offs are things like how much area is included and how much detail is included. So oftentimes when you're collecting information remotely, there's trade-offs. Are you going to collect over a large area, or are you going to collect very detailed data over a smaller area? And there's different types of resolution in remote sensing. There's spatial resolution. That's the one most similar to scale. It's how much area on the ground are you gonna collect. Something called spectral resolution. How much of the electromagnetic spectrum, how many different bands of information are you going to collect? An important concept is temporal resolution. How often can you go back and do measurements in the same place? And then lastly, radiometric resolution, and that's has to do with, we've talked in the past about different kinds of bits with numbers, and this is exactly with that. How many different values can you collect for each measurement? So here's some examples of spatial resolution. So this is a half a meter by half a meter spatial resolution, 1 meter by 1 meter. And it's you probably can't tell much on the screen, but as you go up, start getting into 5 meters and 10 meters and 20 meters, you can see it's becoming more pixelated, right? And then then you're getting up here where you can't really tell what you're looking at because of the level of pixelation. Now, the trade-off is, though, you might ask, why would you want 80 meter by 80 meter if it looks like this? Well, if you're zoomed out, though, if you're covering a large area of the Earth, then this may be a better resolution. So this is not an ideal resolution for looking at this particular neighborhood, but if you were looking at all of North America, that might be a more appropriate resolution. So it's a trade-off between the area covered and the level of detail. Very similar to map scale. Then there's spectral resolution. This is about which bands of the electromagnetic spectrum are you going to include. Typically, the visible bands are each individual primary visible band, like blue, green, and red, are included. Usually a near infrared band. This is beyond what our eyes can see, but is very important for measuring vegetation. And in some cases, satellites can have what's called hyperspectral resolution, where they're measuring even very narrow parts of the electromagnetic spectrum, but even like hundreds of different bands. So that's another consideration. So here we're using both, green, red, and near infrared to come up with a way of visualizing vegetation, like was shown in a YouTube clip that I posted earlier. There is a concept of hyperspectral resolution where this is a imaging system that is on an aircraft that breaks up the electromagnetic spectrum into over 200 bands and very narrowly. So there's different levels of red, different levels of green, different levels of blue, going far into the infrared. And these are used for a special type of analysis where you're really looking at what's called a spectral signature. And these create a very detailed spectral signature because of the high level of spectral resolution. And for spectral signatures, refer to the first video clip I posted as the kind of previewing. And another consideration is how often does the satellite come back? The temporal resolution. Is it 16 days between visits? Is it, a month between visits? Is it view the Earth every day? And so it depends, and what you want kind of depends on what you're studying. So if you're looking at crop yields, you want to have some mix of temporal resolution. You want to have enough to capture different growing seasons, but you want to have a fairly good spectral resolution. So here's a chart where it's like from super detailed to less detailed resolution for spatially, and from quick, rapid turnaround to slow turnaround as far as time period, how many years. So for example, if you're studying geology, you don't need to have the satellite come back every day, because it's not going to change that much. You might need view like every 100 years. But if you're doing emergency response, then you need a much more rapid turnaround of times, on time scale. If you're studying climate of the Earth, you don't need a super high resolution because you're studying the whole Earth. But again, if you're doing like topography or utilities, you need a finer detail. So there's trade-offs depending on the application that you're using it for. Okay, and one thing to be mindful of, and this is a concept we talked about with attribute when we had an extra lecture on attribute tables, and how we talked about how raster data contains numbers, and we talked about bits and bytes, and usually many rasters are 8-bit, meaning there's values from 0 to 255, which is 256 values. But in some cases, you can have satellites collect data that's at higher bits, and it's able to have, instead of having 0 to 255, it can have something like 13,000 different values. And that's called radiometric resolution. And just as we talked about how computers use binary, and you can have, that means it's either a 0 or a 1, that's a single bit. And if you have a 1-bit number, that means you can have 2 values, 0 or 1. If you have 2 bits of numbers, you can have 4 different values. And if you have 3 bits, you can have 8 different values. And you can scale that up. It's an exponential increase that for each additional bit that you include, you have a exponentially increasing amount of values that can be represented for each of those raster cells, or each of the pixels in a satellite image. So while 256 might be fine for many applications, if you're doing, for some remote sensing applications, the satellite can collect at higher levels of bits. So maybe 11 bits or 2,000 different levels, or 16-bit at 65,000, and so on. So that's the concept of radiometric resolution.